Hello students, welcome to my YouTube channel Integrated Physics Studies IPS. एथे मु ऑलरेडी प्लस 2 सेकंड ईयर सिलेबस कंप्लीट कर सारछि। एबे मु प्लस 3 CBCS ऑनलाइन क्लासेस रो वीडियोज गुडा अपलोड करिवि। जदि भल लागिला ताले लाइक कर देबो एवं सब्सक्राइब कर देबो। जो वीडियोज गुडा मु अपलोड करिवि तार नोटिफिकेशन पई एठी बेल आइकन को ऑल रे सेट कर देबो। गोटे इंपोर्टेंट जिंस वीडियोज रो ऊपर एठी जो 3 डॉट्स देखुछो तार क्वालिटी एठी देखो बाय डिफॉल्ट 360 अछि। तमे ताकू पढे मध्ये परिबो। एठी एडवांस रे क्लिक करी तमे रिजोल्यूशन बढ़े परिबो। प्रति वीडियोज रे मु पीडीएफ लिंक देबी ताकू एठी ड्रॉप डाउन लिस्ट रु तमे क्लिक करी डाउनलोड मध्ये करि परिबो पीडीएफ को। लास्ट रे एठी जो मोर चैनल नेम अछि याकू क्लिक करी तमे एठी प्ले लिस्ट को जाई मु प्रति वीडियोज को यूनिट वाइज एज पर सिलेबस सजाई के रखिथिबी तमे सर्च करि परिबो। ओके, थैंक यू।
हेलो स्टूडेंट्स, आज टॉपिक रे हमें एप्लीकेशन ऑफ नानो पार्टिकल्स, क्वांटम डॉट्स, nanowires and thin films विषय रे पढ़िबा इन केस ऑफ योर photonic devices like your LED and solar cell. Now before that, let us have some basic introduction regarding the application of nanomaterials. Now we know that the nanomaterials are actually having dimension in the nanoscale, and these nanomaterials are actually different from other materials because they have a massive surface area, right? Now the nanoparticles are extremely reactive as compared to their larger form because nanomaterials have very high surface area, and this property of nanoparticles is used to create materials with distinctive characteristics for various applications. Suppose we take the example of CNT, that is carbon nanotube. It is a nanomaterial application and they have a very high strength due to higher surface area of its originating materials, right? Now in the nano level, the quantum effects have a higher effect on the behavior of particles, and hence some materials have special effects that have been utilized smartly to produce innovative products. Okay, so the magnetic, electrical and optical properties can be effectively exploited to certain application. For example, suppose in case of gold particle, if we reduce its radius to 2 nanometer, then its melting point can be lowered remarkably, right? So basically the application of nanomaterials can be divided into several categories. Okay, now thin films and engineered surface fall under one dimensional application of nanomaterials, and these materials are used in the field of electronics and chemistry, and they cannot be considered as new materials. Okay, similarly the nanotubes and nanowires fall under two dimensional application of nanomaterials, and here nanowires means these are ultra fine wires or linear arrays of dots that are formed by self assembly, or if we say the semiconductor nanowires, then these are produced by silicon, which is a semiconductor. Okay, then your nanodots and nanoparticles like your dendrimers, which is a synthetic polymer, and fullerenes, which is actually an allotrope of carbon. Okay, so fullerene is having molecules which are made up of carbon atoms. Okay, and it can take shape like that of your tubes or sphere or ellipsoid. So these compounds actually fall into the three-dimensional application of nanomaterials. Okay, and here as I said, the dendrimers are spherical polymeric molecules that are formed through a nanoscale of self-assembly process. Okay, so this is the basic introduction. Now let us see what are photonic devices. Okay, the name photonic comes from obviously use of photon means use of light. Okay, so photonic devices are the electronic devices for creating, manipulating or detecting light. Okay, and these are actually less sensitive to interference. Okay, and examples are like your LED, that is your light emitting diode, then photodiode, then laser diode, solar cells. Okay, so these are the examples of your photonic devices, and these devices can be fabricated using quantum dots, nanowires and thin films. Okay, so let us proceed. Suppose we take the first example, the light emitting diode, that is LED. Now this LED actually emits light spontaneously, and it is constructed through a semiconductor PN junction. Okay, you have already read about the LED from your plus 2 days. So it is an important class of optoelectronic device. Means opto means light and electronic means your electrons. Okay, so it is an optoelectronic device which is available over a wide range of colors. So in this LED, the PN junction, if it is forward biased, then it is emitting visible light in form of photons. Okay, photons, you know that these are the particles of light or the quanta of electromagnetic radiation. Now the energy of each photon which are emitted will be equal to or nearly equal to the band gap of the system, and depending upon the nature of the nanomaterials used, the radiation can be tuned. Okay, tuned means we can control the frequency or wavelength of the radiation across the UV, that is ultraviolet, visible, and IR, that is infrared regions of the spectrum according to our requirement. Okay, so the spectrum of emission will be determined from the electron hole distribution in the nanomaterials. Okay, and this LED is based on the electrical and optical properties. That is why it is called optoelectronic device. Okay, so electrical and optical properties of nanomaterials which are used, and they function by integrating these two properties or the electrical and optical signals. Okay, so LEDs are used in common lighting system nowadays. Okay, so signal processing, then indicator, then light communication system, display, okay, like that of your LED screen, then optical fiber communication system. Okay, so according to the design, the LEDs are classified into two types, namely the surface emitting diodes, and the second one is edge emitting diodes. Okay, so the first one, surface emitting diode, actually emit light radiation spontaneously along the face which is parallel to the PN junction, and light which is emitted along the opposite direction is either absorbed by the substrate or reflected back through metallic contacts. Okay, the second one, which is the edge emitting diode, it emits lights radiation spontaneously along the edge of the PN junction. Okay, and the surface emitting diodes are more effective or efficient because the spatial patterns of the emitted light depends on the geometry of the devices. Okay, but in case of your edge emitting diode, it has a narrow emission pattern which can be improved by using appropriate lenses. Okay, so let us see the schematic diagram of a surface emitting diode which is shown in the figure. Okay, you can see in this figure, at the top and bottom we have the metal contact layer of the device which must be heavily doped and very thin so that it can reduce the contact resistance and allows light to pass through it. Okay, then we have the P plus and N plus layer, and there is a P active layer which is sandwiched between these two. Okay, and finally it is emitting light. Okay, so the P active layer, actually, if we are taking an intrinsic or undoped active layer and it is being sandwiched between the P plus and N plus layer on either side, then the charge carriers are transferred to the intrinsic layer from both the junctions, right? So in practice, the intrinsic layer now becomes doped. Okay, so first initially this was undoped, and in practice when the charge carriers are transferred it will be doped. Okay, so this will result in PN junction and another high low junction that contributes to the charge transfer from both the junction. Okay, so this causes the electron hole recombination, and to prevent the surface recombination, the concept of heterostructures was examined, where the higher band gap heterostructured layers are constructed above and below the active layer. Okay, above and below this active layer, the higher band gap heterostructures layer are constructed. Okay, as per the requirement of doping. Okay, now due to the shift in the band gap, because the band gap will be now shifted, and the diffusion of the injected electrons and injected holes from the active layer will be blocked. Okay, so this was the surface emitting LED. Now the second one, which was the edge emitting LED, here the hetero layers are placed above and below the active layers, and these layers along with the active layer act together in form of a waveguide, right? So a superluminescent diode can now be produced by placing a highly reflective mirror at one end, and this diode can also be arranged to act as a laser by placing two mirrors at both the ends so as to increase the gain. Okay, so the response time of LED is mostly between 2 to 10 nanoseconds, and the LED can be fabricated using nanoparticles, quantum dots, nanowires, and thin films. So let us see the first one, the nanoparticle LED, okay, which is in your syllabus. So here the nanoparticles, as we know, these are the particles between 1 to 100 nanometer in size with a surrounding interfacial layer. Okay, and this layer is an integral part of the nanoscale matter, and it affects all the properties of the nanoparticles. Okay, now this interfacial layer consists of ions, inorganic and organic molecules, and the nanoparticles doesn't refer to individual molecule, rather it usually refer to an inorganic matter. Okay, so the efficiency of LED lighting can be increased by 50% by a technique in which the metallic nanoparticles are prepared into semiconductors. Okay, and in this technique the metallic nanoparticle can be grown both on and below the surface of the semiconductors. Okay, so here the metal nanoparticles can enhance or increase the efficiency of the LED in several ways, and they can act as teeny antennas that alter and redirect the electricity running through the semiconductor. Okay, and tuning more of it into light. Okay, as I said, tuning means you can control the wavelength or frequency of the light. Okay, so you can change the lighting from your UV to visible to infrared region. Okay, so this can also help in reflecting light out of the device and prevent it from being trapped inside and being wasted. Okay, so this technique can be used with a gallium nitride, that is GaN. Okay, GaN, gallium nitride, which is used in LED lighting to boost its efficiency. Okay, and this process can also be used in other semiconductor products, including like your solar cells. We'll study in further. Okay, to boost the efficiency. Okay, so in other technique, the cost of this LED can be reduced by manufacturing the LED with silicon based nanoparticles, and these nanoparticles actually soften the blue light which is emitted by LED and creating the white light, okay, which is the required one. Okay, so this is the nanoparticle LED. Now let us come to the second one, the quantum dot LED. Okay, quantum dot, as you know, these are the semiconductor nanocrystals with optical properties that let their emission color to be tuned from visible to infrared spectrum, and this allows the LED, which is fabricated with the quantum dots, to produce any color of light. So this provides more color options and better color rendering than white LED, because the emission spectrum is much narrower characteristic of quantum confined states. Okay, now there are two types of schemes for excitation of quantum dot, that is in short QD. The first excitation scheme is using the photo excitation with a primary light source LED. Then the second one is the direct electrical excitation. Okay, so in the photo excitation scheme, actually it is a technique in which a blue LED is coated with quantum dots and it glows white in response to the blue light which is emitted from the LED, and this method emits a warm yellowish white light. Okay, so the quantum dots, that is QDs, can also be used in this white LED. Okay, and the quantum dots can be synthesized for LED application, and a light converter can be built on their basis to convert efficiently the blue light into any color of light. Okay, so such quantum dots are used to emit visible or infrared light of any wavelength. Okay, so in QD-LED, that is quantum dot light emitting diode, a layer of quantum dots is sandwiched between the layers of electron which is transporting and holding the transporting materials. Okay, so an applied electric field causes the electrons and holes to move into the quantum dot layer and recombining an exciton that excites the QD, that is quantum dot. So here exciton, as you know, it is a bound state of an electron and a hole which are attracted towards each other by means of electrostatic force, and it is electrically neutral quasi particle that exists inside the semiconductor, and it is regarded as an elementary excitation of condensed matter that can transport energy without transporting the net electrical charge. Okay, so this exciton is actually formed when a photon is absorbed by a semiconductor, and this excites an electron and it jumps to the conduction band from the valence band. Okay, so obviously from the plus 2 days you know that the electron will leave behind a vacant space which is called hole. Okay, which is having the same characteristics as that of the electron. The only difference is that the electron is negatively charged and the hole is positively charged. Okay, so the electron in the conduction band will be attracted towards this hole by means of Coulomb force, and consequently an exciton will be formed. Okay, now the third one is the nanowire LED. So nanowire is a nanostructure with the order of nanometer, that is 10 to the power minus 9 meter, and the ratio of length to width of the nanowire is more than 1000. Okay, it is a structure having a thickness or diameter which is constrained to some tens of nanometer or less, and it has an unconstrained length. Okay, so at nanoscale quantum mechanical effects will be very important, and this nanowire is also known as quantum wire. Okay, there are different types of nanowires such as superconducting nanowire, that is YBCO. So this is a compound which is called yttrium boron copper oxide. Okay, then metallic nanowires like your nickel, platinum, gold. Then semiconducting nanowires like your silicon nitride, tungsten, and gallium nitride. Then your insulating nanowires like silicon dioxide, titanium dioxide. Okay, so molecular nanowires are also there like your deoxyribonucleic acid, that is DNA. Okay, so nanowires are referred to as your one dimensional materials, and in nanowires the electrons are quantum confined laterally and occupy energy levels that are different from the traditional continuum of energy levels or bands which are found in the bulk materials. Okay, so the nanowire LED can be manufactured by fabricating an LED resembling transistor that consists of an iridium nitride. Okay, and iridium nitride nanowire can be stretched between two electrodes on top of a silicon substrate, and this nanowire is about 100 nanometer width and it spans a distance of less than 10 micrometer. Okay, so the nanowires emit light due to the application of current. Okay, so whenever we apply current it will emit light. So the nanowire LED is having more efficiency and has an improved performance, and it can emit infrared light. Okay, so the nanowire LED only, here the electrons are injected and this causes formation of electrons and hole inside the nanowires. And this mechanism is more efficient because a single electron can be used to generate more than one electron hole pair. Okay, so the nanowire LED can emit more intense light than other LED, and it extends the range of colors that can be emitted from nitride based nanowire. And the nanowire LED has a peculiar ability to emit more intense light as the temperature will be increased. Hence, this nanowire LED can be withstand with high temperatures. Okay, so this property of this nanowire LED could be very useful in certain military applications. Okay, then come to the fourth one, the last one, which is the thin film LED. Now we know that the thin film is a layer of material ranging from fractions of nanometer to several micrometers in thickness. And this thin film LED can be fabricated by bonding the LED structure to metallized carrier substrate, and after which the original epitaxial growth substrate will be removed. Okay, so this is achieved by thin film technology, and this thin film LED has an extremely high luminous efficiency. Okay, and it consumes less electrical power, and also it has lower cost. Okay, so this is the LED. Now the second one is the solar cell. Solar cell, you know that it is used to convert the solar energy into useful energy like that of your electrical, then your heat energy. So it is made up of semiconductor PN junction, which helps in conversion of solar radiation into electricity. Okay, so this conversion of sunlight into electricity is based on photovoltaic effect. Okay, so photovoltaic effect means it is the generation of potential difference at the junction of the different materials due to the incident light radiation. So solar cells can be fabricated again using nanoparticles, quantum dots, nanowires and thin films. Okay, so let us see these one by one. So number one is the nanoparticle solar cell. Okay, so it can be fabricated using nanoparticles. Obviously it has lower manufacturing cost and installation cost is also low. Now one of the example of nanoparticle solar cell is the dye-sensitized solar cell, which is made up of ceramic titanium dioxide, that is titania, electrolyte and electrodes. Okay, so the electrodes are here coated with a thin transparent and conductive film which is composed of fluorine doped tin dioxide on glass surface. Okay, so the dye molecules are established on titanium dioxide in order to construct the photosensitized anode, and when sunlight is absorbed by these dye molecule, then excitons will be produced in them. Okay, so these excitons are then passed through nanomaterial titanium dioxide to the outer circuit so that it will constitute electrical current. Okay, so the electrolyte ensures the regeneration of these excitons from the dye molecules. Now the second one is the quantum dot solar cell. Okay, which is fabricated using the quantum dots. Okay, so here the quantum dots obviously absorb sunlight to generate excitons, and it is also based on photovoltaic effect. Also if we see the cost, it is very low. Okay, so the larger dipole moments and enhanced charge carrier separation are the advantages of these quantum dots. Okay, one of the most used solar cell is quantum dots solar cell, which is based on lead sulfide system. Okay, so here the band gap tunability of these solar cell can be extended to cover up the far infrared region of the solar spectrum. Okay, and these quantum dots can easily be synthesized through solution synthesis, and hence they can be readily transferred over the desired substrate through spin coating. Okay, so these quantum dots can also be implemented in single junction solar cell in order to absorb the solar radiation and hence to convert them into electricity. Okay, then let us move further. The third one is the nanowire solar cell, which are fabricated using semiconductor nanowires. And here the nanowires absorb solar radiation to generate the excitons. Okay, these nanowire solar cell are having high power conversion efficiency, and the conversion of solar radiation into electricity is based again on the photovoltaic effect. Okay, so recently the semiconductor nanowires have received a very great interest for their potential application to the case of solar cell. Okay, silicon nanowire, that is in short SINW, can be used for the fabrication of a nanowire solar cell. Okay, now the last one is the thin film solar cell, which is made by depositing one or more thin layers or thin film of photovoltaic material on a substrate like that of your glass, plastic or metal. Okay, so here amorphous thin film silicon, that is in short ASI TFSI. Okay, here A is for amorphous, TF is for thin film. Okay, then your cadmium telluride, in short CDTE. Okay, then CIGS, that is copper indium gallium diselenide. These are used in the fabrication of thin film solar cell. Okay, and these thin film solar cell actually is much thinner than the crystalline solar cell. It is flexible and having lower weight. It is used in solar panels and it is cheaper, means less costly. But however, it has less efficiency than that of the crystalline solar cell. Okay, so this is all about the applications of nanoparticles, quantum dots, nanowires, and thin films in case of your photonic devices like your LEDs and solar cell. Now I have taken these from another book, but however it has given only two applications, that is of quantum dots and your nanowires. Okay, so here you can study it for your knowledge purpose. You can see the quantum dots in solar cells, then it has given in a detail, then quantum dots in LEDs. Okay, besides these two, it has also given the application of quantum dots in case of your display technologies like that of your mobile screen, then LED TV screen and tablet monitor. Okay, then medical application, where in case of your cancer detection and surgery the quantum dots are being used. Okay, then the second one is the application of nanowires. Similarly, it has given its application in case of your solar cells along with its advantages. Okay, advantages and drawbacks. Okay, then finally the application of nanowires in case of your LEDs. Okay, so you can study it for your knowledge purpose and accordingly make your note. Okay.
Thank you.